In last few classes, I tried to give you the definitions of vector space, subspace of a vector space, what is a real coordinate space, and we also discussed on subspaces associated with a matrix A in context of solving x is equal to b. We discussed about column space, and in context of solving the homogeneous equation A x is equal to 0, we discussed about null space. What we have seen there is that, for example, the column space in case of a matrix which has 3 columns can be expressed as combination of linear combination of these 3 columns, or any vector belonging to the column space can be given as a linear combination of 3 columns. In case one of these 3 columns is dependent on other 2, any column space vector can be given as a linear combination of first 2 columns. The third column is also a linear combination of first 2 columns in that case. We have also seen for null space, we find out what are the free variables and what are the pivot variables in reduced to echelon form, and depending on the number of free variables we get null space vectors, and we told that the null space is again a linear combination of these null space vectors. And we have seen that in case of 2 null space vectors, null space can be thought of a plane or linear combination of 2 vectors. In case of 1 null space vector, null space can be thought of a line. In case there is 0 vector in null space is only the origin or only a point. Now, what are the number of vectors or minimum number of vectors which can be utilized to define a particular subspace? In some of the examples, we have seen 1 or 2 null space vectors are needed to define the entire null space, or all column vectors or few column vectors are needed to define the entire column space. So, how is this number of vector determined, and how does it determines the shape of the space? That is one point of interest. So, in today's class, we will start look into few definitions which will probably answer these questions, and in the next class or next to next class, we will, depending on the pace of the instruction, we will see, we will discuss on how these definitions of what are the minimum number of vectors to define a space is relevant for a particular matrix and also for a matrix equation. So, we will come to today's topic, which is linear independence, basis and dimension in terms of a vector space. Linear independence is given as, suppose there are k vectors v1, v2 up to vk, and these vectors are added as a linear combination, each vector is multiplied with a constant and then they are added. And if this addition is 0, c1 v1 plus c2 v2 plus ck vk, if this is 0, and if this happens only when c1 is equal to c2 is equal to ck, all the coefficients which are multiplying it is 0, then these vectors are called linearly independent. That means, I cannot write any vector vi as a linear combination of a1 v1 plus a2 v2 a k vk except the ith term. I cannot express one particular vector vi as a linear combination of other vectors, and then we say that none of the vectors are resultant of other vectors, and this is a linearly independent set. The converse is a linearly dependent set when one of these vectors or one or more of the vectors are resultant of few vectors here, and that is given as that if any of the c's are non-zero, then these v's are linearly dependent, one vector is a combination of other. So, if all the c's are 0, we cannot take sum of this in the right hand side and divide by another c, because everything is 0 and it will give a 0 by 0 form. But if any of these c's are non-zero, then we will get a dependent set of vectors and we call them to be a linearly dependent set. What are the examples? One is 1 0 0 1. they are linearly independent. If I think of a 2D space x and y, this is say 1 0 and this is 0 1, one vector here and another vector here. Obviously, the vector along y is not a result anyway is not related with vector along x, it cannot be, they cannot be expressed in that way. So, they are linearly dependent. Similarly, if I think of a vector 1 1, that is also linearly dependent on 1 0, because there is an y component and 1 0 of 1 1, 1 0 does not have an y component. So, I cannot combine them. In when which case they will be linearly dependent. If there is two vector, they are linearly dependent, means one vector is just multiplier of the other vector. So, if 1 0 and 3 0 are there, so one vector is 1 0 and the other vector is along the same line 3 0, which is just multiplication of that. So, we can write 1 0 1 into 1 0 plus minus 3 into minus 1 by 3 plus minus 1 by 3 minus of that. So, erase it 1 3 plus minus of 1 by 3 of 3 0, this is 0 0. So, they are not linearly independent, they are linearly dependent. Similarly, if we think 3 vectors all in R 2 1 0 0 1 2 3, anything 2 3 any vector 2 3 can be expressed as a linear combination of 1 1 and 0 1, I plus 2 I plus 3 j. So, this is also a linearly dependent set. So, in a nutshell, if the one of the vector can be expressed as linear combination of any other vectors or at least multiplication of any of the other vectors, then it is a linearly independent, then it is a linearly dependent set. In case we have a 0 vector, for example, I take this case 1 2 3 4 5 0 and 0 0 0, that is always a linearly independent set, because I will multiply anything 0 with this plus 0 with this plus any number say 5 with this will give me 0 0 0. So, if there is any 0 vector, 0 is anyway linearly dependent on other vectors. I can have any vector and combine them, multiply them with something, add them and subtract similar vector from them and get 0. So, any set of vectors with a 0 vector is always a linearly independent set, because I will put a non-zero number in front of 0 and will get 0. So, any set of vectors with or not with which includes a 0 vector is always linearly dependent. So, anywhere I have a 0 vector in the entire set, I will end up in a linearly dependent set. If we have a set of n plus p vectors in a real coordinate space R n, where p is greater than n. So, if we have vectors in R n and we have more than n vectors in R n, they will be always linearly independent. So, we have a case like that, we have 3 vectors and of course, the third vector we can very easily inspect and tell it can be expressed as linear combination of first two vectors, because all these vectors are belonging to R2, or all these vectors have two components. So, if we write the equation that C1 into first vector plus C2 into second vector plus C3 into third vector is 0 0, and when we write this in the matrix form, this is nothing but a null space equation. This becomes a null space equation of the matrix V, and there are number of columns which is greater than number of rows. So, we will end up in a reduced row echelon form. Remember, we have done it in the previous class, which will be say something like 1 0, some non-zero number here, or maybe a 0 number here, then 0 1 and maybe another non-zero number here into C1, C2, C3. So, C3 will become a free variable. These are the pivots, free variable, and will give me at least one, in this case, non-zero null space vector. So, we will get a non-zero null space, and non-zero null space means C1, C2, C3 is not equal to 0. Therefore, this set becomes a linearly independent set. V matrix will have maximum 2 pivots in Rref, as there are 2 rows only. Hence, at least one free variable will be there, and there will be non-zero null space. So, linear independence and linear dependence is related with the null space also. If we can express this vector, combine all these vectors and write a matrix, and the null space of the matrix becomes 0, then the vectors are linearly dependent. If there is any non-zero null space of that matrix which consists combination of all the vectors, all the column vectors as the columns of the matrix, then we have a non-zero null space will mean that there is a linearly independent set. These vectors are not linearly independent. Non-zero null space will assert that these vectors are linearly dependent. So, it becomes important for us to look into null space vectors. So, hence C1, C2, hence at least one of the free variables are there is at least one free variable and one non-zero null space, and the C1, C2, C3 becomes non-zero. So, it becomes important for us to look into null space vectors. If columns of A are independent, then null space vector is 0. Columns of A are independent, then null space vector is 0. If they are dependent, then non-zero null space exists, and the vice versa. So, we look into an example. A is 300, 410, 152, and we try to solve AC is equal to 0, and if the null space solution is 0 only, there is only one solution which is 0, then we can write the columns as a function of C1 as C1 into first column plus C2 into second column plus C3 into third column is 0, and C1, C2, C3 will be 0, which is a null space solution. So, depending on the null space, we can determine whether the columns are linearly dependent or independent. If we have the null space vector is equal to 0, only one null space vector which is 0, then it is a linearly independent set. If there is no non-zero, at least one non-zero null space vector, then it is a linearly independent set. For example, if we take one vector with one matrix with dependent columns 2, 1, 4, 2, the columns are dependent on each other, and write C1, C2 is equal to 0, 0, and we can clearly see that C1 is equal to minus C2 is one answer. So, C1, C2 minus C1 is equal to minus 2 C1 is equal to C1 is 1 and C2, right. So, C1 will be C1 is equal to minus 2 C2, minus 2 C2. So, C1 C2 is equal to minus 2 and 1, that is one answer. C1 C2 is equal to minus 6 and 3, that is another answer. However, there are non-zero C1 C2 for which this satisfies, therefore, we can say 2 1 and 4 2 are linearly dependent. So, we go to next slide and see what happens with linear dependence and independence. If the columns are linearly dependent, before going to next slide we can probably discuss here, if the columns are linearly dependent, then one column can be expressed as linear combination of other columns, or when we will try to find out determinant, we will find the determinant is 0. So, for linearly dependent columns, the matrix will have a 0 determinant, and we will see it in the next slide. For dependent columns or row, the geometric dimension of the space becomes less than n, where n is the dimension of the real coordinate space. For example, if I have a linear, and the determinant is volume of the space contained within the geometry. So, we will write that determinant, if we recall the definition of determinant, it is volume of the space contained by the vectors. So, if we have 3 independent vectors, for example, I have 1 1 0 0 along I, 0 1 0 0 0 1, these 3 independent vectors. The volume, we can find it out, that will be the determinant, the volume will give us the determinant, which is determinant will be 1. If 2 vectors are linearly dependent, so the third vector, or one vector is linearly dependent on the third vector. So, what will happen, we will same have this 3 dimensional geometry R3, this is one vector, this is the other vector, say this is vector A, this is vector B, and this is vector C. So, the space contained by them is a plane and it has volume 0. So, when we will remember getting dot product, we took volume created by the space enclosed by the space, that is multiple dot product of the area vector with one of the vectors. So, dot product of this area vector with the vector C, which is again in this area, will be 0. So, determinant will be 0 and the matrix will be singular. So, what we can say, for a singular matrix, the columns or the rows are dependent, and we have seen it in the discussion on determinants also, that if we make one column or one row combination of other columns or other rows, then we will get a 0 determinant. 0 vector is linearly dependent on any other vector, and we have discussed earlier that any set of vectors where I have one 0 vector must be a linearly dependent set, because we have C1 into one vector plus C2 into another vector is 0, and we make C2 non-zero, make C1 0, we again get a 0 0 combination. So, 0 0 is all, if we have this vector 0 0, we will always end up V1 1 V1 2 0 0, they are linearly So, you get any set, and also if I have a 0 0 here and we look into the determinants that I have in x y coordinate x y, which is R2, I have one vector say V11, V12, and I have another vector which is origin 0 0. So, what is the area contained by this? Area will be 0 because it is a vector and a point, it does not, we cannot encompass any area by drawing a parallelogram with these two vectors. So, area will be 0, that is determinant is 0, therefore, this will be 0 is also a linearly dependent vector. Now, we come to another definition, what is spanning, and that is an important definition regarding column space and null space, because when we are showing the form of any vector in column space or any vector in null space, we are writing it as the any null space vector is combination of two null space vector that came out using two free variables in the first example we did that. So, we say that these two null space vectors which came out using the true free variables span over the entire null space. If we know these two vectors, we can linearly combine them and then we can get any vector in the null space, entire null space. So, if a vector space V consists of all linear combinations of W1 to Wk, then these vectors span the space. Every vector in V, vector V in the space capital V is some linear combination of W's. So, we can write any vector V, we can write any vector V which is belonging to capital V as the linear combination of W's, and then we will say that W span the entire space, the set of W vectors. That is, if we can write V is equal to C1 W1 plus C2 Ck Wk for some of the coefficients Ci, and then we will say that V is capital V is a space which is spanned by W provided small v exists in capital V. So, can all the C's be 0? Yes, 0 vector is very much part of any vector space. So, if we look into capital V vector space, 0 vector is a part of that. So, we will put all C1 to Ck everything 0 and we will get 0 vector which is also part of that. So, C can have any value, C can have any real value, and we will get one particular vector for one particular set of real values of C, we will get one particular vector in V, and that is why with infinite values of the combination C1 to Ck, we can get infinite vectors in V and we will get a vector space. So, except one important thing is that except the 0 vector, if I consider 0 vector to be a 0 dimensional vector space, except the 0 vector, any vector space also must have infinite vectors. That is one important definition out of it, because it will be spanned by some vectors. Spanning means those vectors which are spanning this space. So, when linearly combined, we will get one vector in the vector space, and this linear combination can be done in infinite ways, assuming any arbitrary value of C1 to Ck. So, you should get infinite vectors in the space V. Column, now we look into the column space. Column space is spanned by columns of A. For example, we have the vector matrix A 147, 256 and 360 are the column vectors. Any vector in any vector in row space, this is given in terms of row space, but again row space is also formed. So, you can also write row space is spanned by rows of. So, we look into the row space or row space of A, which is linear combination of the rows of A. So, if we make any arbitrary choice of alpha, beta and gamma, we should get one vector which is lying on the row space. So, when we looked into the null space, this is important, that spanning of null space vectors found using free variables span the null space. So, we took one of the free variables 1 and remaining 0, we get one vector. We take another free variable to be 1 and remaining 0, we get another null space vector. And so, that way we get all the if there are n free vectors, n free variables, we will get n null space vectors, and these n vectors span the entire null space. So, the number of free variables is equal to number of vectors spanning the null space. And if we use, we have to find out all the free variables and vectors associated with obtained using all the free variables. These vectors, the number of free variables will determine the number of these vectors, and they will say to be spanning the null space. And that also justifies writing a vector space using this expression, because if we know the vectors which are spanning this space, now we know about all the vectors, location of all the vectors in the real coordinate space, which will be the orientation or location of the particular vector space. R3 is spanned by vectors 1 0 0, 0 1 0 and 0 0 1. R3 can be also spanned by vectors 1 0 0, 0 3 2, 0 0 4, or even by 4 vectors 1 2 3, 0 2 3, 1 4 6 3 3 1. In any case, we can linearly combine these vectors using any arbitrary constant and get any vector belonging to real coordinate space R3. However, so this is like I can use this axis and linearly combine them to get any vector here. I can also use the axis like 1 0 0, this is fine, 0 3 2, so some vector here, and 0 0 4, some vector here. This thing and again can form this vector by linearly combine these vectors. I can access this and add one more vector and again linearly combine them. This will be a redundant vector, but still I can have the linear combination and find any vector in R3. However, so there has to be minimum 3 vectors to define any vector in R3 to give the spanning of R3. In case we have 0 1 0 or 2 3 0, we will be able to, so we have same R3 with the vector 0 1 0, which is say here, and 2 3 0. I can only define any vector belonging to this particular plane. I cannot obtain a vector by linearly vector like this, which is has a component in the z direction by combining these two vectors. So, they do not span R3. Similarly, 0 1 2, 0 2 4, 0 3 4, though there are 3 vectors, all these vectors have a 0 in the x direction. So, all these vectors lie in this plane, they do not span R3. So, what we need? We have to have 3 vectors to span R3, minimum 3 vectors. We can have more vectors, but these 3 vectors, like here these 3 they are linearly dependent. These 3 vectors cannot be linearly dependent. So, there has to be a minimum number of independent vectors to span a subspace. If we have less than that many vectors, we cannot span the subspace. We can have same number of vectors, but if they are not linearly independent, then also we cannot span the subspace. More vectors can also span a space. 3 linearly independent vector can span R3, but 4 vectors they are also spanning R3, but the minimum number is there, which is determined by the number of independent vectors which can span the entire space. So, we will continue with the discussion of spanning and see that linear independence and spanning, when both are satisfied, we get a new set of vectors which is called basis for a vector space. We will discuss about this in the next class. Thank you.